Hi, this is Kaylee Shacklock, and this is my Lab 3, Black Hole in Orbits. Introduction. The purpose of the lab was to estimate the mass of the black hole for the first part anyway. My final number ended up being 1.4 times 10 to the 34 kilograms. Some fundamental principles and models were Newton's second law, which is given by F equals the change in position over the change in time. Gravitational force in the equation is given. Newton's second law describes how fast momentum changes and with time, which was used to compute the net force acting on the star, and the gravitational force calculates the force that the two masses attract to one another and is used to find the final mass of the black hole. The system was a star, and the surrounding was the black hole and everything else. And the initial conditions was the mass of the star, the time interval, which I used this number of seconds in the day, and the position of the black hole, which was at the origin. Code. This is all of my edited code. This code loops the motion of the star and then calculates the net force acting on the star, which is then used to estimate the mass of the black hole. This section of the code creates the arrows and updates them as t increases. The arrows represent the forces acting on the star, and since they're all multiplied by the force, their length and their size are to scale. Results. This is what my final screen looked like. Each of the arrows are kind of small, which kind of scared me at first, but then when I realized we were working with really large units, and in perspective with the distance, the numbers start becoming a lot smaller because the size of the star is incredibly small compared to the distance. So when you take that into account, it kind of makes sense that the arrows are relatively small. Part 2 was the initial velocity. The second part of the lab asked us to take in a planet, moon, and spaceship, and with the given conditions, determine the initial velocity of the spaceship. And this was my edited code for that. And this was the initial velocity that it successfully ran. So the value of x was 80,000, and the value for y was 15,000. What does it mean? In this lab, both the net force and the change in momentum are equal despite coming from two different equations and concepts. Change in momentum is calculated using position over change in time, while the net force is calculated using the sum of all the forces acting on the object. When things are broken down into parallel and perpendicular components, we can determine that the parallel components depict speed, while the perpendicular predicts the motion. What if the interaction of mass, position, and velocity of each of these objects have effect on the gravitational force occurring between each of the objects, but the black hole and the star, along with the planet and the moon force, have the biggest bodies at the closest distances, resulting in the black hole impacts the star's motion while the planet impacts the moon's orbit. And my room for error, I wasn't completely sure if my code was right, and my delta t was difficult to choose, so my choice could have been incorrect. Instead of using all of the total seconds in a day, it definitely could have been something different. I know in the original code it was like 0.05, but when I tried that, it didn't work. And then the last thing was that no non-gravitational forces were included in this calculation. Thank you so much for watching. Bye bye.